Hello, today we are going to discuss and show friction. We know that friction can be created between people, but we're going to study the kind of friction between two surfaces. And the way we're going to discuss it is we have a mass that's lying on a flat surface right here, and we are going to pull sideways on it, in other words, parallel to the two surfaces. Friction is caused by the unevenness of a surface. The smoother surface is, the less friction. We all know that. And the rougher it is, the more friction. The reason for that is that the uneven surfaces bump against one another and have to go up and down a little bit to clear each other. So the rougher the surface, the more it has to go up and down, and therefore the more friction is created. Now, we have a mass here, and it is going to be pulled in the direction of the plane of the friction, and it has a weight. The mass has a weight. We just multiply m by little g, the acceleration due to gravity, and that gives us the weight, which is a force. Mass itself is not a force, but this is a force, which we call weight, which a lot of us battle with all the time, present company included. There is a thing called the coefficient of friction. The coefficient of friction, mu, is a ratio of the force needed to pull the object against friction to its actual weight. You know that if you have an empty box and you pull on it sideways across the rug, it might take a pound or two of force to do it. But in this particular case, if you put stuff in the box, it's more massive and weighs more, you have to pull on it harder or push on it, whichever the case would be. But the force has to be bigger. Well, what is the ratio of the force needed to pull something against friction or push it as opposed to how much it weighs? It's actually a force-to-force ratio where we have it here. The force is measured in newtons, perhaps, and the weight can also be measured in newtons. It's a force over force ratio. Force that way compared to force that way. Now, if you had a coefficient of friction of 1, you would have to pull it with as much force as its own weight. If you have a coefficient of friction that is 2, you would have to pull it with twice the amount of its own weight. In other words, the two surfaces would need to be glued together just about, because the most you're going to pull something is its weight. If you pull it straight up, then the whole weight is bearing as a load. So in order to get higher than a coefficient of 1 for your friction, you have to put some glue in here, or some rubber cement or something in here. Really gotta yank, so that you're actually pulling with more force than you are its own weight. I seem to get into those circumstances once in a while. Now, how do we measure the force of sliding friction? How do we actually measure that? Well, we use a scale. This is the kind of scale that you'd weigh a little fish on. It's a spring scale. You hang something here, the more mass it has, and therefore the more weight, then it pulls the little spring thingy down. But you can also use this sideways. I can take this block and put it on a wooden board, which is what it's on. It's got more friction than on this counter. Plus, I can measure it easier. Now I'm going to tie this. I have 2 hooks to put them together, and I'm going to put a mass on here. Let's see if I can use the right one. Put a mass on here which will help press the things together. So the weight is now the weight of this wood plus the mass of this times little g. The total weight is the weight of the block and the weight of this brass thingy that I have. So that's the force down. Now, how do I get the force sideways? Real simple. I just pull on this and look at the dial. I've already done this, so I know the figures. You pull on it until it starts moving. When it starts moving, it overcomes the friction. Now, you know it takes more push or pull to start something going than to keep it going. Once it's moving, Once you overcome that, what we call static friction, you then just have sliding friction. Look, I'm pulling this out and it starts moving. But just to keep it going at a constant velocity, not accelerating, because that takes more force, that's a little less. It's hard to get the car pushed to get it started, but then once it's rolling, it's a lot less. Right now, we're just going to show how you get static friction. That's the friction that it takes to overcome its own friction, the force that it takes to overcome its own friction, and to get it going. There it goes. It was sticky. Yeah, there we go again. And you just read the dial. Now what I've done, I'm going to back up so that you can see this. What I've done is created a graph. And in that graph we have the weight down on the x-axis, and then we have the force sideways, the pulling force in newtons, both cases, that it would take. And I've already done this and plotted the points. This was 1 Newton, 2 Newtons, 3, and 4. I forgot to put them in. That consisted the weight. I mean, 4 Newtons is 9.8 Newtons is 2.2 pounds. So 4 Newtons is about a pound. 4.5 Newtons is about a pound. So it's a little bit less than a pound. So here, it took 1/2 of a Newton to pull it sideways. So I plotted a point. For 2 Newtons piled on there, it took a full Newton to pull it. And so forth. 3 Newtons took 1.5 Newtons to pull it. 4 Newtons took 2 Newtons to pull it. If you make a graph, it's a very straight line. I rounded these off, by the way, a little bit. It's not going to be exactly a straight line when you do it, but it'll be close if you do it right. It's all as accurate as your instruments. Now, if you take delta y over delta x, the rise over the run, you get the slope of this. And the slope, let's just take it, we shouldn't do this, 20 over 4, 2.0, I forgot to put the decimal, over 4 would be your slope. So 2 over 4 would be 0.5. If you do it for all those points, you'll see that the slope comes out to 0.5, which is a 45-degree angle. So to start this thing moving, this block, no matter what weight you put on it, it all comes out to a linear relationship where it takes 50%, 0.5 is 50% of its own weight to get it started. So the coefficient of friction is 0.5 or 50%. So if you wanted to make that into a formula, you would say that the pulling force, F sub P, let's call it, pulling force, is equal to the coefficient of friction, which is 0.5, determined from this, times the weight, the force down. And there you have it. Now what about sliding friction? Sliding friction is measured with the same apparatus, the same variable weights, yet what you would do is you would just wait until it goes at a constant rate. You'd get it going and just keep it going at a constant rate. You would then replot this graph. You'd make a data table, a new data table, and you would replot this graph so that you would get a new coefficient. In fact, what you would find out is that the coefficient of sliding friction for every amount of weight you got is going to be less, which just makes sense. It takes less force to, again, to push something, or in this case pull it, than it does to get it started. And there we go. What you can do at home is get yourself a little scale. They sell these at hardware stores. And you can do this experiment without any real difficulty. This one here is old. It's already been pre-stretched. I guess if you hang a fish you catch on this, you can lie about how big it was. Okay, thank you very much, and we hope you enjoyed the presentation.